Last time, we rescaled a random walk until the jagged path looked smooth. Take that limit seriously, as an actual continuous time process, and you get Brownian motion. First described by a botanist watching pollen jitter in water, then explained by Einstein as molecular collisions, then formalized by Wiener as pure mathematics. 3 names for the same object. Brownian motion, W of t, is defined by 3 properties. It starts at 0. W of 0 equals 0. Its increments are independent and normally distributed. For s less than t, W of t minus W of s is normal with mean 0, and variance t minus s, exactly the scaling limit we built last time. And its paths are continuous. No jumps ever. Unlike the Poisson process, nothing here happens all at once. 2 consequences fall right out. The variance at time t is var of W of t equals t. The typical size of the wandering grows like root t, the same square root law from the random walk. And it's self-similar, rescale time by a constant c and space by root c, and W of ct over root c is again a Brownian motion. Zoom in or out, and the statistics never change. That self-similarity is why the limit of the random walk had to look the way it did, at every scale at once. Here's the strange part. Brownian motion is continuous everywhere, but differentiable nowhere, not at a single point. Zoom into any piece of the path, however small, and it looks just as jagged as the whole thing. There's no scale at which it ever smooths out into a straight line. Ordinary length along the path is infinite, but its quadratic variation, the sum of squared increments, is exactly t, the quantity that makes stochastic calculus possible. Einstein used exactly this model in 1905 to explain Brownian motion physically. Pollen jostled by unseen molecular collisions, its variance growing linearly with time. Evidence, at the time, that atoms were real. Finance uses a relative, geometric Brownian motion, where the log price moves as a Brownian motion. It underlies the Black-Scholes option pricing model. And underneath both, W of t is a martingale. Its best forecast of the future, given the present, is exactly where it is right now. Brownian motion, the continuous time limit of a random walk with independent Gaussian increments, continuous but nowhere differentiable paths, and a self-similar, scale-free structure. It's the bridge from discrete probability into continuous time stochastic calculus, diffusion, finance, and beyond. Next, martingales. The general idea of a fair game that Brownian motion turns out to be an example of, and the last piece of this section.